This video is for section 9-4, exponential functions and logarithmic functions. The function that has this form to it, where b is the base of a power and b is not 0 or 1, is called an exponential function. Here's an example exponential function. Y equals 10 to the x. The value of the base is 10. The exponent is x. When x is 3, what's y equal? Well, that would be 10 to the third power, which is 1,000. Exponential functions are one-to-one. For each x value you input, you get one y value paired to it. Because it's one-to-one, it has an inverse function, and that's called a logarithm. So the word logarithm is kind of a weird sounding word, but what it is the inverse of an exponent. Here's an example logarithmic expression. Here's how you speak it. Log base 10 of 1,000. And this happens to equal to 3. Here's why it's equal to 3. Because the log is the inverse of an exponential, when you find the logarithm of a number, what you're finding is the exponent that you raise the base to equal that number. To evaluate this logarithm, you'd ask yourself a mental question like this. 10 to what exponent makes 1,000? And that's why the answer is 3. The value of a logarithm is the same thing as the exponent of the exponential function. Here's that same statement repeated, but using the symbols. Log base b of a is the exponent in this exponential function. With that idea, we can evaluate logarithm expressions. Let's find what log base 3 of 9 is. Here's how you do it. It is the exponent in this exponential function. 3 to what power equals 9? And that answer is 2. Let's evaluate log base 5 of 125. The base of the logarithm is the 5. The value of the logarithm, the thing we're trying to figure out, is an exponent. What exponent do you raise to get 125? That would be a 3, because 5 to the third power is 125. Next example, what's the base of the logarithm? It's the a. When we evaluate a logarithm, when we find out what it's equal to, we're trying to find out an exponent. What exponent do you need to make a to the 20th power? What's that exponent have to be? It has to be a 20. Because the exponential function and the logarithmic function are inverses, their graphs are going to be symmetrical with respect to the line y equals x. That was one of yesterday's main ideas. Let's do an example of that. Let's graph this exponential function. We'll do that in green ink. And then let's graph this log expression in blue ink. So the green one first. Y equals 2 to the x. To graph that function, we could make an xy table. A good number to choose for x when you're doing exponentials is to choose 0, because that's going to find us the y-intercept. What is 2 to the 0 power? It makes 1. Now another good number to use would be 1. What is 2 to the first power? That's 2. Hey, what's another easy number to substitute in for x? How about putting in a 2? So y would equal 2 squared, which is 4. You know, that base is pretty small. I bet we could even plug in a 3, and the answer we get is not going to be too large that it's going to go off the top of the grid. So what's y equal when x is 3? That makes 8. Don't forget some negative values. So what is 2 to the negative 1? The meaning of a negative exponent is reciprocal. So this makes 1 over 2. If we kept going backwards, now we would get 1 over 4. If we went backwards one more spot, we would get 1 over 8. Let's graph those dots. -1, 1/2 is located here. 0, 1 is located here. 1, 2 is here. 2, 4, and then 3, 8. Start out right alongside the x-axis, that's the asymptote line, and then swing up through the dots. This green curve is the graph of y equals 2 to the x. Now, let's graph y equals log base 2 of x. Let's make that graph by finding the reflection of the green curve over the line y equals x. So first, we better draw the line y equals x. It goes uphill at a 45-degree angle through the corners of all the squares. Now, in blue ink, let's graph this logarithm function. It's the inverse of the green one. Let's find the mirror image of every dot on the green curve. Like this y-intercept dot right here. When you travel across the brown line, you end up at this spot. Remember, the other way to think about it is interchanging the x and y values. If this green dot is 0, 1, then its inverse is 1, 0. And that's where I put the blue dot. Where's the inverse of this dot? Travel straight across that brown line, and you end up right here. Where's the inverse of this green dot? Travel straight across that brown line, and you end up here. Where's the inverse for this dot? Well, this dot is at 3, 8, so the inverse is 8, 3. Over 8, up 3. Hey, there was one more dot, and we did not find its mirror image. That was this dot right here. This is at -1, 1/2. So if you switch those, you get 1/2, -1. And that's located here. Now let's draw a curve through those blue dots. What does it look like our asymptote line is going to be? It's going to be the y-axis. So draw alongside the y-axis without ever touching it. The blue curve is the reflection of the green curve. These are inverses of each other. The graph of a log function has the y-axis as an asymptote, and once you cross over the x-axis, it begins to swing out towards the right. Another way to make the graph of a log function is to make an xy table and choose numbers for x. Like if x was 1, what's the answer for this log function when you put a 1 where x is? You would ask 2 to what power makes 1? And that answer is 0. Or what if x was 2? You would ask 2 to what power makes 2? And you would get an answer of 1. Or what if x was 4? You would ask yourself 2 to what power makes a 4? And you would get an answer of 2. If you tried to put in x as 0, what would you get for y? 2 to what power makes 0? There isn't one. That's undefined. And that's why on our graph, we never actually touched where x was 0. The y-axis was an asymptote to our graph. Looking at this graph, what's the domain of a log function? What x values are you allowed to have? X is greater than 0. What's the equation of the asymptote? Well, the asymptote is the vertical y-axis line. So the equation of that is x equals 0. Here's an example. Determine the value of x if we have this logarithmic equation. Do you notice how they have the same base? So because the logs have the same base, what do you think's true about those two expressions? They have to be equal to each other. And that allows us to write this equation, which hopefully you recognize as a normal quadratic equation. Add 1 to both sides, we get x squared equals 9. Then use square root to get x alone. We have the positive and negative square root of 9, which is equal to positive or negative 3. Let's summarize the lesson. We discussed logarithms. They're the inverses of exponentials. And the way you evaluate a logarithm is by asking yourself what exponent is needed. For instance, if you wanted to evaluate log base 4 of 64, you would ask yourself, 4 to what exponent makes 64? And that's a 3, because 4 to the third power is 64. We also graphed logarithms. They have this general shape that you see in blue ink.